In this lesson, I want to show how functional programming is like Unix command pipelines, or vice versa, how Unix command pipelines are like functional programming. I want to start with this quote here. So I found this quote in a book called Masterminds of Programming, and it's from one of the creators of the awk programming language. And a really interesting thing is it says that pipes, command pipelines, facilitated function composition on the command line. So we talk about function composition a lot in functional programming. So what this says is you could take some sort of input, perform a transformation on it, and then pipe the output of that into another program. And then you could do the same thing again with that next program. So that next program would also take its input, perform a transformation on it, and produce that as output, which could again be piped into something else. And you'll see as we go through this how much this is like functional programming. And so now what I want to look at, I have two goals for this lesson. One is what I just stated. We want to think of writing functional programs as being like writing Unix command pipelines, and that's goal number one. And then the other one is later in this lesson, I will look at how we can look at our code visually to help us think in terms of functional programming. So as I scroll down here, this is an example that we're going to go through. So in this paragraph here, I talk about your boss comes to you and he says, I need a script that's going to tell me how many unique users are logged into a Unix system at any given time. So if you're not familiar with Unix, I'm going to show you how to do all of this. If you are familiar with Unix, then you can start thinking about this if you don't know how to do it already. But knowing Unix, I know that I'm going to start with the who command. That's going to be my data source. And who is not really a pure command because it's going to reach out into the outside world and it's going to find out who is logged into this system. And then it's going to report that in a format like this. So to start showing things, let me start moving things around here a little bit. So I just happen to have a who command set up over here, and it's going to give us that same output that we have right here so we can follow along directly with the book. An important thing about the output is that it's structured and consistent, so we can look at that like that and say, okay, well, at least we have a source of information. And remember that we're looking for unique users, so we see that Joe is repeated here a couple times. So we're going to want to reduce those multiple Joes down to one Joe as part of our solution. So I'll come over here, and the algorithm appears to be something like run the who command, get this list of usernames from that first column, then reduce that down to the unique usernames, and then count the size of that remaining list. And in Unix, the way we do that is we're going to chain these commands together. So we start with who, then we're going to use a command like cut to get the names from that first column. And I made a mistake in the book here, and the unique command won't work by default, but I'll show you what will work. And then we'll get a count of those unique usernames. So the first thing we want to do is get the usernames from this first column. And to do that, we use this cut command. So let me do that. So I'll say who, and I'm going to pipe that into this command. So I'll use a -D option. And then I want to do -F1. So before I hit return, -D is looking for a field delimiter. So I'm saying that look for a space for the field delimiter. So it comes over here and it says AL, and there's a bunch of spaces, then console, some spaces, then OCT, so on. So it's actually looking at this white space in this column, this one, and this one right here. And that's how it's going to separate these columns for our purposes. And then what I'm saying here is I just want field number 1. So this will be field 1 right there. So if I hit enter, you'll see that. And if I were to change that to 2, you would see that kind of information. So I think that's happening because there are multiple blank spaces there. So I may have to go even further to 3 and 4 and so on. I think what you actually do there is you would use the tab character, but I am not going to get into that. Let me just come back to here and reduce that to there. So again, we had the who command giving us that information, and then this command pipeline giving us this information right here. So that takes me through the first step, and I have now this list of usernames. And as I mentioned, now what I want to do is reduce that down to get only the unique usernames here. So the way I would do that is pipe this again. So now I want to pipe that. And I mentioned that unique does not work. The actual solution is to use the sort command, sort-u like this. And that does give us the unique usernames right here like that. So again, we start with this source of data right here. We pipe that into this command right here. And that command does its work. And then we pipe that output into this command, and it does its work. And that gives us this output right here. So now we have the number of unique users. And that's what I was going through in the book over here. And now that we have the number of unique users, we actually just want to count this number of rows. So one thing I didn't mention is you could think of this as being a list over here. So this is the first element in the list, or the first row in the list, the second row, and the third row, and so on. So now we have this list of 4 names over here. You could think of that as being a list of 4 strings. Now we have that down to a list of 3. And the way we count those in the Unix world is we would pipe that into the word count command and then say count the number of lines. That's what that -L means. And so now we have that down to 3. And I was pausing there for a moment because I noticed that word count doesn't sound like it does what it does. But as I mentioned with the -L option, that means count the number of lines that you're receiving. So this received 3 lines. And the thing I don't like right here, and when I first started working on the solution, it was I didn't realize that this information was going to be padded like that. So what I have to do is come back over here to the book and say, well, what's going on with those leading spaces and how do I get rid of those leading spaces? And the way you do that is with this command here. TR stands for translate. So now what I want to do is pipe that into one more thing. So that's going to be translate. -D means delete this character. So I want to delete blank spaces from this string. So TR is receiving this as a string, or you could think of it as a list with one element and the 3 is right padded. But I would think of it as a string. And now we want to delete those blank spaces. And now this is actually what I would like right there, like that. It's just the number of 3 by itself. No leading spaces like right here. So that is the solution. And I don't want to get into it too much more at this moment because I'm going to talk about this more visually in just a few moments. But one thing I do is I note that if you're going to write this as a Unix shell script, the verbose version of it would look like this. So we would start with the who command. We would get result 1, result 2, result 3. And that's what we would be looking at over here is we'd have the who command would be the first one right there, that first one. Then the result from this cut command would look like this. That's what would be stored in res1 over here. Res2 would be this one right here, and res3 and res4 and so on. So all I'm trying to do over here is show what this would look like as a Unix shell script if I wrote it in a verbose manner and we had variables for each line. And then finally at the end, we would echo that. And then what I do is I say, well, that looks suspiciously like a series of expressions followed by a print statement, doesn't it? And so then some equivalent Scala code might look like this. So we would get a who variable. We would call a function an impure function named getUsers. That would give us a sequence of strings. Then we would call a cut function like that. That would give us res1. We would call a unique function with that result. That would give us res2. Count lines would give us res3. And then trim on that would give us res4. And then we print res4 right there. So note, this is actually very common in functional programming, is you'll start with some impure source of data like this. And I'll talk much more about impure functions later in this course. But right now, just think of this as getting data from some impure function, then pure function, pure function, pure function, pure function, followed by a statement here to produce our output. And again, this is an impure function that prints out to the outside world in this case. And now as I keep talking about Scala here, what I note on the next page is that we can start combining these expressions because they are pure. So what we can do is get rid of these intermediate variables like res1. So I eliminate res1 as an intermediate variable. And I say, well, start with that who command, pass that result into cut, and then pass that result into unique. And that's how I get rid of res1 is this right here is exactly equivalent to res1. So that's how we get rid of that. And then I keep working through that process. And now I get rid of res2 because it's an intermediate variable. And I can take all of that and plug it right into here. And we'll get this count lines code right here. So you can see this snippet of code is just being passed in right here like that into count lines. And then I do the same thing on the next line. I eliminate res3. And then finally, there are no more intermediate variables. So it might make sense to rename res4 to number of users like that. And then if you want to combine that with the print statement, you would finally get this code right here. So all I'm trying to do right there is show how this Unix code right here could be equivalent to Scala code like this. And down here I have a note that code like this right here looks a lot like Lisp, the programming language Lisp, Lisp right there. And the way you read Lisp code is you start with the inside. So this is where you get the data on the inside. And then you see that we apply the cut function to that result. And then we apply unique to that, count lines to that, and so on. So that's the way you read Lisp code. And I happened to use that a long time ago. So whenever I see code like that, it starts to make me laugh a little bit. And then the other thing I note here is you don't have to use this condensed style. You can use this style that I start with up here, or you can use this style down here. Either one, whichever you prefer when you're writing functional programming code. And now my second goal in this lesson is to show what this looks like visually. So that's where we're going to start getting into here. And I mentioned this earlier, but you can think of the who command as being generating a list of strings right here. So who command is right here. That's kind of sort of my symbol for a database or a data source right there. And then from that data source, we're getting a data stream. And that data stream we can think of as being a sequence of string in Scala. So that comes into a pure function named cut. Cut performs a transformation on that data, and it produces a new sequence of strings. And then we pipe that sequence of string data into unique, again, another transformer function. It produces a sequence of string as a result. Again, that was actually sort -u. I need to make that correction. And it produces another sequence of string. Finally, that sequence of string is piped into the WC command, and we get one string out of that. And then the problem with that was it was left padded. So then we pipe that data into the TR command, and then that gives us this final result, which you could think of as being an integer in Scala. And visually, this is what a lot of functional programs look like, is you have some type of data source over here, and then some other communication with the outside world over here. And then everything in between is a series of transformation functions. Another important thing is that the data always flows in one direction. In this case, it's just going from left to right. So the data starts here, it goes here, then it flows here, flows here, flows here. The important part is it never flows backwards, and then we never mutate the data. So I don't mutate any data here that affects something over here, etc. We don't mutate the data, we just transform it. So we have this input stream of data coming in here. We work on that data to produce new string over here. And then in this function, we work on this data, and that produces a new data stream over here. But again, there's no mutation of the data anywhere in here. And that's exactly how functional programming works. And I go into that a little bit more here, where the WC command is a pure function. And actually, all of these functions, cut, unique, WC, TR, these are all pure functions up here. And each one of those are pure because they take some kind of data sources input. They don't rely on any other hidden state or hidden values anywhere else in the world. They just work on that stream of data that they're given. They don't read or write to any files. They don't alter the state of anything else in the universe. As I mentioned, they don't mutate the data. Their output depends only on their input. And another thing I didn't mention is that given the same input at various points in time, they always return the same value. So if we go back up here, cut will always return the same data up here, and this command pipeline will always return this same information. But I should say that when given this input right here, cut will always produce this output right there. That's what I mean by this statement right here. And again, we could think of this as getting input data from some outside source, in this case, the who command. Then it goes through this series of pure transformations that I showed. And then in Scala, I use the print line statement to produce our output. So as I scroll down here, things I already mentioned, data flows in only one direction. Data that a function is given as input is never modified. This one I didn't talk about too much, but you can think of functions as having a front door or an entrance and then an exit, but there are no side doors. There's no windows for data to slip in or out of. And these are all important properties of pure functions and Unix commands. If you like visuals, this is another look at that visual information. So we started off with this input data source or this data stream. We went through a series of transformations, again, in one direction. So these are all transformers, and then we get our final result, and then we printed that to the outside world. And then I show the slightly different way here. We start off with that data source. We go through a series of pure transformations. The data only flows in one direction, and we get our output. And then I talked about this before, where data is never modified. It's never mutated. So we start off with this data. We don't come over here and say, oh, I'm going to try to go back and change Al's name to something else or change Joe's name to something else. We don't do anything like that. We take data in, we work on that data inside of here, and then we produce new data as a result. And we think of this as being like a transformer our pure functions are transformers of that data, so we produce new data, and then the same thing happens over and over again until we get our final result. And then on this page, I created this as a symbol for a pure function. So I need to do that better with it, like a door here and another door here. But basically, a pure function named WC has an entrance. Data comes in only over here. And notice I broke this down. So this function would have two arguments. One would be a sequence of strings, and then the other one was like a -L option for WC. So you could think of these as being two parameters coming into WC. And then WC works on this data, and then it produces a result through the exit here. And what I mean by this is there are no side doors here or windows, so data doesn't leak out over here, and data doesn't magically come in over here or anything like that. Data comes in the front, goes out the back, is what I mean by the symbol. And I note this here, you can think of pipelines as being combinators. So you'll hear the word combinator when we talk about functional programming. And basically what's going on here is combinator you can think of as meaning combining commands. It actually means a bit more than that, but for right now you just think of this as combining commands. So I'm combining this command with this one, with this one, this one, this one to produce what I want. So whenever you think of combinator, just think of combining. Again, to some people it means a bit more than that, but if you want to keep it simple, we can think of it that way. Another thing to note is that if I had structured my Scala code differently, I could have made it look like this. So we could start off with the who command and then passed in the delimiter and saying field one, and then call .unique on that, then call WC on that, and then TR on that. And again, the reason I show this is because we hear that word combinator quite a bit in functional programming. And really all it means is that you're going to have code like this or you're going to have code like this. So I just wanted to show both of those approaches in this example. This is another case of where you hear a word like combinator and you think, well, that sounds kind of scary. But again, it's just something simple. You're combining functions here or here to create a solution. Now, I just want to mention two more things about this particular problem or this example. And one was that our thinking followed these steps. So we started with a problem statement. We wanted to know how many unique users are logged into the system. And then what we did was we thought about, well, where is the data source for this information? Where can I get that from? That, of course, turned out to be the who command over here. And then depending on your thought process, in this case, you could think of the who output as being a multi-line string or a list of strings. And I prefer to think of it as a list of string or a sequence of strings myself. And then because you knew the structure of the who data and you know all these other Unix commands, you know that you can apply them together, something like this or like this to create your solution. And the reason I mention that is because that's exactly what the functional programming thought process is like. You start with some kind of problem to solve. You're either going to know where the data source is or you're going to need to figure that out. Then you're going to need to understand the format of the data. And then you want to know the end result or the end goal. What is it you're trying to aim for? In this case, it was the output that you wanted. And then to get this output right here, you apply a series of pure functions to that input data source to transform the initial data into the final data structure that you want. And then in this case, if all the functions you need already exist, use them just like we did over here. Otherwise, you write your own new pure functions to transform the data as you need to. And again, to summarize that, this Unix thought process that I show up here at the top for this specific Unix example is exactly the same as the functional programming thought process that I show right here. As a little bit of an aside, I have a note here that we use the word apply a lot in functional programming. So functional programmers say that we like to apply functions to input data to get to a desired output. And as you saw in the previous discussion, using the word apply is very natural when we do that. Then there are some more exercises here. So if you want to exercise your functional programming thought process muscle, take a look at these exercises here and see what you can do about them. For instance, write a pipeline to show the number of processes owned by the root user. And if you're not familiar with Unix, that will start off with the PS command. So you want to take a look at that one. That's going to be your data source for that. On this next one, I show write a pipeline to show the number of open network connections. Back in the day, I used to use netstat as the data source here. And now I think you can also use LSOF as a data source for that. And then I show a few more exercises here. One last thing I want to note is that the diagrams I showed here were actually based on something called data flow diagrams back in the old days. They used to call them DFDs. And there are a few formal notations for DFDs, but because I don't 100% like them, I use my own here. So if I was going to draw this myself using my own data flow diagram technique here, I like to draw data flows as streams. So that's what I mean by stream. Looks a little bit like a stream or a creek or something like that. Then I like to annotate streams with their data types. So you see this should probably say a list of strings, but I do have that here. So here's our data stream right here. And then I annotate that as being, okay, this is a sequence of string coming into this pure function right here. And then we come out of that pure function with another stream right here. So this is our new sequence of strings. And that comes in a unique or sort-u, and that comes out of there, again, another stream, and so on. So I'll call this a DFD-like sketch of the Unix command pipeline solution that I just showed. And then, as I mentioned earlier, I like to draw functions as rectangles because of the whole front door and back door thing. So here I use the rectangle as a symbol for a function, in this case, the cut function. And I also show the data that comes in. So we have a sequence of string coming in, and then you could think of this as being two parameters that are coming into the cut function like that. And I do want to say that I don't draw every program out like this, but I do when they get hard. So a lot of things you can do in your brain, but when things get harder, that's when you might get on a whiteboard and you're sketching things out with other people. Then I will use this type of approach right here where I sketch out a solution and using all these data flows and these transformers. Another important thing about these drawings and then showing the types of data right here, I get into here is there's a really interesting book. It's an older book now, but it was called Complete Systems Analysis. I think it probably came out during the 1990s or maybe early 2000s. They had a really nice rule they called the conservation of data. And it said that each process or function in the data flow diagram must be able to produce the output data flow from its input. And what that means right here is if you look at this one's a little bit simpler. Again, this was the sort-u. This function right here must be able to produce this output from this input. And that was a nice way for people. If you think about systems analysts, it's a nice way for them to look visually at a data source. And then they can think, well, can I produce this output here from this input? And well, you think, okay, yeah, well, I definitely can. This is just a sequence of strings. This is another sequence of strings that all I'm doing is getting a unique one. So yes, I can produce this output from this input. So that's what they mean by conservation of data. You can't have something that magically appears over here based on this input over here. And that's another way of saying that unique can't have any side doors. There can't be other data coming in here or over here. Data just comes in here, goes out there. And they showed their diagramming process looked a little bit like this. So they would say the who command consists of this data right here. So if I go back over here and say the who command, it consists of the username, the terminal, and then the date and time information over here. So that's the way they would document their data if you want to go through that type of thing. And along with that rule of data conservation, in another place, there were some slides, some PowerPoint slides at DePaul.edu that I found, and they used a different term. They call it black holes and miracles. So they made these observations about data flow, and they said data stays at rest unless it's moved by a process. And then the second one is interesting. It said processes, or you can think of functions, cannot consume or create data. So the first one here says you must have at least one input data flow to avoid miracles. So you could think of this first one as meaning you cannot have a pure function that takes no input parameters. A function can not have zero input parameters and then produce data and be a pure function. That just doesn't work. So that's what they talk about by avoiding miracles. And then a pure function must have an output data flow, and they call this to avoid black holes. So for one like this, you can think of now as a Scala function that returns the unit data type. That means that the data went somewhere into some black hole, and you don't know where it went to. It may have been printed out, it may have gone into a database or a file, but because there was no output data flow from your function, they refer to that as a black hole. So I really like the combination of this rule of data conservation along with this thought process of avoiding miracles and black holes. And again, as a quick summary, I just showed that writing Unix pipeline commands is like writing functional code. And I showed several different ways to do that. And I'll just stick with this diagram right now. And I showed that we start with some type of data source. We have the stream of data that we work with. We have pure functions that transform that data, and they produce new data streams, another pure function, and so on. And I won't go through the whole process again, but I will say that this is probably my favorite type of data diagram out of all the ones that I showed. And I showed in the comparison to writing functional code, we have data sources or input that bring external data into your application. Those are not necessarily pure functions. But then everything else we work with inside is a series of pure functions, and you can think of those as being transformation functions. We apply as many of these transformation functions as we need to get the data in the format we want, and then we output that result when we're ready. And then finally, we combine Unix commands with pipelines in the same way that we use pure functions as combinators. And I showed that type of thing right over here in this example from the Unix world. And then if we scroll back here, we see that same type of solution with this Scala code right here, as well as the earlier Scala example I showed, which was in this code here, all the way down through this code here.